All right, so let's move on a little bit. And before we get into hazards and emergency management specifically, let's talk about the intelligence agenda. This is some stuff that Lowenthal talked quite a bit about in reading this week. So every country, of course, has their specific intelligence agenda related to defense and national security, but there are some items on the intelligence agenda that are really shared across most countries. So GEOINT plays a role in a lot of these, like international agenda items. Cyberspace is a big one. Terrorism, obviously, is a big deal. Weapons of mass destruction, proliferation, narcotics, and then hazards and emergency management as well. One of those really international problems that most countries are trying to solve in some capacity or another. So let's talk about cyberspace, kind of go through these different domain areas a little bit, just so you kind of get a sense of the problems that a lot of people are dealing with, and maybe a little bit of a sense of how GEOINT can get involved. So one of the things you'll hear any computer scientists talk about or be able to talk about is Moore's law, right? This is like their foundational theory, right? And the basic idea behind this is that the number of transistors in an integrated circuit doubles approximately every 2 years. It's named after Gordon Moore, who's a co-founder of Intel. So beyond that kind of very specific meaning, what this is really describing is the exponential growth of digital technologies, right? The fact that technology, the power of technology increases exponentially, and that there are going to be related social and economic changes as the technology changes as well. So again, kind of a foundational law of computer science, and also a foundational law of the entire technology world now. So here's a graph that kind of gives you the example of what Moore's law looks like based on the computer chips that have been developed over the years. And you can see there's your exponential scale on the y-axis there, and there are your years in a linear scale, right? So there's definitely been exponential growth in the transistor counts on microprocessors, aka the power of computers, as we've moved forward. So a little bit about the role of GEOINT in relationship to the cyberspace intelligence agenda item. So one thing to think about is commercial versus government capabilities, right? Most of your decision makers, and even more so the end users, I would say, are expecting the Google Maps and Google Earth experience in finding information using a map. That's not realistic for government capabilities. It's just not. There's so much more that happens in that domain that needs to happen beyond what your commercial capabilities can provide. So I've always found that setting expectations is the key, right? The user says, I want the Google Map experience for this particular system that you're building. And sometimes your job is going to be to tell them, no, you can't have that, and here's why, right? They probably won't like it, but whatever, sometimes hard words have to come out. Another thing to think about is bandwidth, right? So this is really a key factor in our ability to disseminate GEOINT products. And the bottom line is that high-resolution imagery requires high bandwidth, right? This imagery is the original big data. I always like to say that because it's true. So tiling, which we talked about in an earlier lecture, and converting raster imagery into vector products, those are really key workarounds dealing with bandwidth issues. And just kind of speaking from the perspective of the Army Geospatial Center, we had Kevin Bach in last time to talk about that. That's one of the critical challenges they're dealing with, is bandwidth as you get down to the platoon or squad level. There's just not the network there to be able to send high-resolution imagery back and forth. There's not enough bandwidth. So another big topic, general topic area is cloud-based analytics. So the idea of having these parallelized computer clusters, aka the cloud, you can use those to solve a lot of spatial problems in a fraction of the time that it used to take. So there's an incredible amount of power there to solve problems. But the key is making sense of the big data, right? I mean, it's one thing to be able to solve a problem. It's another thing to understand what problem should be solved. So that's part of the challenge. And as I mentioned earlier, GEON is the original big data. So things like image processing really benefit from cloud-based analytics and having parallelized computer, or parallelized, not paralyzed. Paralyzed would be bad. Parallelized computer clusters. I spelled it right. I said it wrong. So let's talk about attribution a little bit, right? So when you think about attribution, the classic example in kind of the cyber arena would be where is a cyber attack coming from, right? Who is responsible for trying to hack into this government system, right? Think about attribution. The related GEOINT question, which we dealt with a little bit in our lab exam, was where's my data coming from, right? Finding the data is fairly easy. I think I overstated a little bit by saying it's easy. Finding geospatial is not easy, but you can find something usually. But finding reliable data and proper metadata is hard. So you can usually find something that'll work if you just want to make a basic map of the states in the US, right? But if you wanted really good data attached to that shapefile, that would be a lot harder. And verification and validation are key, right? Key part of making sure that your data is coming from a reliable source. Let's talk about our various domains on the internet that we might look at to try and find data. And here I've got our little Facebook icons to describe my general sense of finding data at these various domains. So my .com example here, Digital Globe is actually a pretty amazing data source. So hence the thumbs up and the wow face. The sad part comes in, the smaller sad guy comes in that it can be very expensive, right? If you're lucky enough to work at a government agency that has paid for access to all of these wonderful Digital Globe holdings, you will find that their data, their imagery is quite good. It covers pretty much anywhere in the world, and the user interface that you go through to get it, at least the one that I've used in the past, is awesome. And probably one of the best user interfaces, the most intuitive user interfaces out there. So, you know, another .com, here we go, Google Maps. Don't put Google Maps in your lab and call it a product. I'm probably going to laugh at it, hence the laughing face. And then the angry face there is in that a lot of people will automatically accept this as truth, even though this imagery, or as the truth in terms of what's on the ground right now, specify, when the reality is that this imagery could be 3 years old, right? So for figuring out where McDonald's is that's been there for 10 years and the best way to get there from your house, perfect. For any real GEOINT application, I mean, even for that, what was it? It was ConAgra Foods was the business that was located. I would have probably, if it was me doing that project and not trying to do it in 2.5 hours, but actually doing it as a real task that somebody had given me, I definitely would have followed up on a phone call to that business. And to figure out what that feature would be, I probably would have just asked them. Probably would have said, you know. Anyway, that's neither here nor there because that was beyond the realm of the possible for your 2.5-hour time window that you had to do the lab. But point being that Google Maps know the limitations of this or Bing Maps or any of the other major online commercial mapping services. So let's go to another .com. This is freegisdata.com. This one, sorry, it only gets the sad face. It is possible to find good things on here if you dig a lot, but there is typically a lot of junk on these websites and a lot of things that you really just can't rely on because they've gone through many, many different transformations. The major upside here is that they do have this big disclaimer in the pink box there saying, beware, the data linked to below may be inaccurate, incomplete, or just plain wrong, right? Yeah. So you are given warning. And like I said, I've found good data through sites like this before, but for the GEOG professional, I would stick with Digital Globe probably, or one of our nice government sources. So, .org websites, those can be a good source depending on what the organization is, right? So here we have the Habitat Institute, and the good thing about the GIS data that you'll find on sites like this is usually there's a person, they describe their methodology for collecting the data very well, and there's usually a person that you can actually call or email and talk to about the data they have on their site. And sometimes this type of data can be very useful depending on the problem that you're trying to apply to. So all in all, I would say, most of the time, these, nonprofit, NGO type organizations can have some of the nicest data sets, depending on the problem you're trying to solve. You're not going to find global imagery coverage on this website, but you might find, in this example, a very interesting habitat assessment or land cover assessment that would be hard to find anywhere else. .edu, usually pretty good. This is usually, academic departments, University of Oregon, libraries, in this case was the one that I found, which has some downloaded GIS data. We get a little sad face on here because they say data is presented as is. We accept no responsibility for its accuracy. And when possible, metadata is included. So not up to the standard usually met by federal agency where they have to have certain metadata in there. Yeah. But that being said, all in all, this data is usually pretty good source. A lot of times it's rehosted. So a lot of times these sites will be rehosting data that's available through the federal government. But sometimes you can find something good. So overall, thumbs up. Your .gov, it gets the heart because usually this is your best stuff. And you can absolutely find stuff on the government websites like the NASA website, Earth Observatory website that you can't find anywhere else, right? And that is timely and meets the specific purpose that you need it for. I'll talk a little bit more about this particular data that I'm showing on the screen here. So there we go. It gets the Facebook heart. It also gets the Facebook wow factor because, like I said, you can find stuff on here that is literally exactly what you need and, is incredibly timely and meets those metadata and meets very robust metadata and accuracy standards that are well established and published. It gets a little bit of an angry face here because the user interfaces that you need to use to download this stuff can sometimes be beyond frustrating, right? I think that the national map is actually a pretty good user interface. Apparently, they're retiring that user interface and are going to revamp it. I think it's pretty good as these .gov data interfaces go, but you'll find some pretty brutal ones. Sometimes you'll even find just a file folder that you go and click the files you want to download from, which is useful if you know exactly what you're looking for, but if you don't know exactly what you're looking for, it's basically worthless. So that's my spiel about knowing your domains. Let's take a closer look at this image. Any guesses as to what this is?
Clouds and that's the Gulf Coast stretching from Louisiana to like the South Padre area.
Nice. Yeah. Good catch. So going back here, this is actually the zoomed out image where there's a before and after. I'm trying to remember exactly what sensor this came from, and I can't remember off the top of my head. I don't think I have it written out here. But we've got some very cool, it might be MODIS, again, don't quote me. I don't remember exactly which satellite this came from. But this is a before and after Hurricane Harvey imagery set of the Gulf Coast of Texas and Louisiana. And it's a false color image, right? This isn't like, obviously the land is not this bright green and the clouds aren't
blue.
aren't quite that blue, right? But what it highlights is, well, that looks like a hurricane coming through. And what it highlights even better is the extent of the flooding that happened, right?
Jeez.
So this really gives you an incredible look, I think, at damage that was done, the flooding damage that was done by this hurricane. And this is the type of data set that, when CNN makes their change map, or the New York Times, or whoever, wherever you like to look to get your info about natural disaster and hazard impacts, when they make their change map, this is the data set that they're using. But the cool thing about this NASA website is you can actually go and get the raw data and do your own analysis of it if you want to.
Yeah.
So really, really good stuff that you can find here.
Wow.
Let's move on to our next intelligence agenda item, international intelligence agenda item, terrorism. So as you guys, I'm sure, are well aware, GEON is really critical in predicting, preventing, or responding to asymmetric threats like terrorist attacks. We've got a lot of different things we do with GEON here: imagery interpretation, multispectral analysis, 3D modeling, persistent surveillance, simulation, increasingly pattern recognition and facial analysis, especially now that we have such nice FMV and drone capabilities, and link analysis networks, which is going to be our topic for next week. There's a screenshot on the right. I think I already talked through the Bin Laden compound raid and how NGA helped design this realistic 3D model to help in the mission planning for that. So kind of just one example of the type of 3D modeling that can be done to support efforts to combat terrorism. Weapons of mass destruction proliferation. This isn't a topic that's quite as hot in the news anymore. I mean, I guess it's hot in terms of talking about North Korea, but remember, especially back in whenever that was, 2002, 2003, when they were ramping up for the second Iraq war, WMD was the hot button issue, right? So the reality here is that GEON is often the only means to see what is actually happening. When we talked about the Cuban Missile Crisis, that was a great example, right? When they couldn't fly the U-2 over Cuba because of cloud cover or because of diplomatic restrictions, then when they couldn't see anything for a few days because of cloud cover, they had no clue what was going on the ground, right? Most important thing to keep in mind is even because you think you see something doesn't mean that's actually what's on the ground. Most GEON is subject to interpretation. Going back to the second Iraqi war, the weapons of mass destruction factories that were supposed to be in Iraq and that were identified using imagery actually didn't exist, right? So somebody thought they saw something on the ground, didn't actually end up being there when we went in and looked for it. GEON really plays a secondary role to human intelligence in terms of monitoring and verification, just because, again, there's only so much that you can interpret from an image. Sometimes you have to be on the ground. And bottom line is that nuclear weapons proliferation has to be stopped early before a viable deterrent can be established. When you think about, nuclear weapons specifically, right? In the case of Iraq and Iran, right, they didn't get very far with their nuclear programs, and therefore there was a viable deterrent to them continuing to develop them because they didn't have the capability. Once a country has the capability, like North Korea keeps on demonstrating, the deterrent really doesn't exist. It's more in their national strategic interest to build up their program more, right? So it's one of those things where early detection and analysis using GEOINT can be key in stopping WMD proliferation. Talk a little bit about narcotics. So there's this connection between illegal narcotics operations and terrorism. So, for example, opium profits in Afghanistan have been used, were funneled into Al Qaeda, and cocaine profits were used in Colombia to fund all kinds of nasty stuff that happened there during their very long guerrilla war, 30-year guerrilla war in Colombia. So, in my view, this is more of a domestic policy issue than an international problem. I mean, it's become an international problem because many countries have chosen to make narcotics illegal. But, and again, this is, in my view, where demand exists, supply follows, right? So if you think about it from purely an economic perspective, there's a reason this problem is so persistent, right? And seems like the more you do, the less success you have some of the time. One of the interesting GEOINT applications here is that you can use multispectral remote sensing to identify narcotics crops. Like you can literally see marijuana plantations from space using remote sensing imagery, right? And identify the unique spectral signatures that that plant has. So it was actually, I know for a time that was used out in California to find large grow operations. Of course, it's legal there now, so kind of a moot point. But back before it was legalized there, there was some work doing that. Other roles for GEOINT in this domain space, so you can obviously detect heat in the infrared band. So for illegal indoor growing of marijuana, that would be one of the GEOINT things. And then, of course, video surveillance for any kind of a criminal network, including a narcotics distribution network, can be very helpful. All right, so let's move on to the main topic that I want to focus on for the rest of the lecture today, which is hazards and emergency management. So GEOINT plays a critical role in this domain, really is essential for protecting people from hazardous events like floods, wildfires, tsunamis, hurricanes, industrial accidents, and terrorist attacks. And there's really, when you talk about the terminology of hazards, there's kind of three different categories you could establish. There's natural hazards, where you think about like a tsunami, hurricane, tornado, earthquake, something that is pretty much going to happen no matter what people do. Doesn't mean that people can't impact through their actions these events, but they've been happening before people were on the planet, will probably be happening long afterward. There's what we consider human hazards, like a chemical spill or a terrorist attack. And then there's these coupled hazards too, right? So if you think about what happened in Japan in 2011, we had a nuclear accident caused by a tsunami, right? Or for Hurricane Katrina in New Orleans, flooding caused by a levee break, right? So these are kind of coupled hazards. And of course, these categories are arbitrary and fluid. They're not hard, there's not really hard divisions between each of them. And the bottom line is that all hazards can be characterized by both physical and social vulnerability. These are two terms I'll talk about just a little bit. First, I want to talk about what a disaster is, because this would be another term you see thrown out there a lot. I like this definition, Smith, 2004, I forget the name of the paper. But their definition is an event concentrated in time and space in which a community experiences severe danger and disruption of its essential functions, accompanied by widespread human, material, or environmental losses, which often exceed the ability of the community to cope without external assistance. And I really think the last part of that definition is key, right? Exceed the ability of the community to cope. If you have a river that overflows its banks, but you have a very robust levee system in place, the town located behind those levees may not be impacted by that flood stage at all, right? So that would be a hazard, but not a disaster. When the water goes over those levees, you are probably going to have a disaster on your hands. So a hazard, that's a good definition from Susan Cutter, who's a very famous geographer, University of South Carolina. But a hazard is basically any natural, question?
I said nice.
Oh, okay.
South Carolina. Good things about that school.
Okay, yeah. Yeah, they've got a very good GIS program there, and very focused on hazards and natural disasters too, partially because she's there. She's pretty much, when you talk about hazards, she's like the thought leader in that area. Kind of came up with it, most of it herself, honestly, working with her grad students. So a hazard you can think of as any natural or technological threat to people or things that they value. I like that simple definition, pretty clean. And then risk you can think of as the product of the probability of a hazard occurring and the vulnerability of the people affected by this hazard, right? So the risk really has these two components of what's the likelihood of this hazard happening, and then how well can people cope with this, right? What is their vulnerability to the hazard? So moving on to another term that I've used a few times already, just to give it a more formal definition, vulnerability, right? So vulnerability is just simply the potential for loss. You can talk about physical vulnerability, where that really refers to the likelihood of exposure to a given hazard, right? So what's the likelihood that your house will be flooded if the river hits flood stage, right? And then social vulnerability is the likelihood of adverse outcomes. So continuing along with our flood example here, if your house gets flooded, will you have the insurance to replace everything in your house? Will you be able to get out of the house before it floods? Will you or someone you love be injured or killed by this, right? So, and that's really kind of the major difference. Is physical is really more the physical characteristics of the hazard. Social, it has a lot of other factors that go into determining what will happen to a person, right, or a group of people. The bottom line is that there are a lot of emergency management techniques out there, but most of them are really targeted towards reducing vulnerability and preventing a hazard from becoming a disaster, right? So the example that we'd really point to here would be an emergency evacuation, right? Emergency evacuation is going to change physical vulnerability to your hazard and social vulnerability as well, just by removing those people from the area that's likely to be affected. So moving on from kind of the more, I would say, academic focus of hazards, vulnerability, and disasters into the related but more applied domain of emergency management. So typically, we think about 4 stages of emergency management: preparedness, mitigation, response, and recovery. And below this, we can see this nice chart which kind of shows that these 4 stages definitely happen in a cycle, right? But it's a continuing cycle. One phase definitely feeds into the other. And then at the very center of this chart, you see hazards analysis, and just showing that basically your analysis of hazards, whether it's using GEOINT techniques or however you want to analyze them, really can help contribute to each of these 4 stages of emergency management. So, GEOINT specifically for emergency management can be used to inform decision-making during all 4 of these stages, right? So, in the preparedness stage, for example, how can we quantify a hazard, right? Classic GEOINT application here would be, let's fly a plane into a hurricane and see what the wind speed is, right? How strong are the winds going to be in this hurricane, right? That's miles per hour is a very nice number to be aware of when you're planning for a hurricane making landfall. And then, of course, on the preparedness side, there's the idea of identifying vulnerable populations, right? Pull up, in the U.S. at least, you pull up some census data, get down to an appropriate spatial resolution, probably block group level or census tract level at a minimum, and you can see where people of lower incomes or older populations are, and they're usually people that fall into those 2 categories are more vulnerable to a hazard. At the mitigation phase, you can think about something like, what are the best evacuation routes, right? Another type of GEOINT analysis that you would do, probably using some type of network science approach. That's something that we're going to get into in the next lecture. Actually, I think we talk about a little bit in this lecture. Okay. God, I was getting ahead of myself. And then this question of like, how robust is critical infrastructure, right? So how old are our levees? How tall are they? How much of a flood can they withstand, right? The response phase, we'd be thinking about, or the response stage more appropriately, we'd be thinking about what is the best way to warn people, right? How can we let this massive population know that a hazard is approaching? And then also thinking about how many people need to be rescued and where are they, right? There's very obvious GEOINT applications there, and flying a helicopter over an affected area and figuring out where people are. And right, exactly, search and rescue. And then at the recovery stage, you could do a post-disaster assessment, really looking at the critical infrastructure that's been damaged, and then also, trying to figure out when is it safe for your evacuees to return, right? These are just a few examples. There's any number of questions that can be addressed using GEOINT that fit into all 4 of these stages. So let's dig a little bit deeper into defining these 4 stages of emergency management. So the goal of your preparedness activities is to build operational capability for disaster response, including emergency operations planning, personnel training, early warning systems, and communication networks, right? So those would be kind of the primary areas you'd focus on when you're at this preparedness stage. Here's your classic example. Thank you, U.S. Department of Homeland Security, for letting us know that there will be a test of the emergency. I don't know why they're, emergency alert system, that's why. The EAS, not the emergency broadcast system, which is the one that I always remembered from growing up. Yeah. But anyway, this would be your classic way to alert people that there is an approaching hazard. Where I grew up in Wisconsin, we had tornado sirens that would go off when there was a tornado warning. So I remember a few times hearing those growing up. Thankfully, a tornado never touched down, but you knew when there was a danger, and you'd hear the sirens and you go down in the basement. Be like, all right, well, there we go. Hopefully this thing doesn't hit our house. So talking about mitigation, really the goal here is to reduce the long-term risk of vulnerable populations. So this can be something like zoning decisions or building and safety codes, insurance, or hazard mapping, right? Hazard mapping is definitely a component of insurance, and usually zoning, building and safety codes, zoning decisions, maybe more of a political thing, or maybe sometimes, people are allowed to build houses in places where they probably shouldn't, because there's a deep-pocketed developer that has friends in the local legislature, and there you go. Sure, build an entire housing tract right at the wildland urban interface. We're not too worried about it. Santa Rosa, California, right? So anyway, sorry, no more editorializing. Here's a pretty classic GeoG product that there's actually a very robust flood mapping infrastructure in the U.S., or floodplain mapping infrastructure in the U.S. This is actually a Canadian map showing, it's really hard to see. I can't even read the legend, so sorry about that. But basic idea is this is showing flood risk. So, yeah, just an example, not anything that we need to study up on, but one of the cool things about this map too is look at those pictures that they have over on the right-hand side. Like they've got a picture of the river at normal levels and then at flood stage, right? So it's kind of like, here's the map that shows you the risk. Now here's the reality of what might happen or what has happened in the past. Moving on to emergency response. So these are actions that are taken in the immediate time periods before, during, or after a hazard, including warnings, evacuations, sheltering, and search and rescue. Your preparedness largely determines your response capabilities, right? So in order to have a successful search and rescue, you have to have usually people who understand that it's their job to undertake this mission and are pre-positioned at locations that A, won't be completely cut off by the hazard that they're trying to deal with, and B, have enough supplies and other equipment to allow them to do their job.
Yeah.
So here's an example of a response activity, namely an emergency evacuation. This is, I'm trying to remember, I believe Hurricane Ivan in 2004. Apologize, I don't remember exactly what this picture was taken from. But this is when there was a massive evacuation ordered in Texas due to an approaching hurricane. And one of the techniques that they employed that you can see very clearly here is that they switched the direction of flow on roads and highways to move people out of the area. Therefore, dramatically increasing the capacity. The issue that they had is they ordered too many people to evacuate all at the same time. Therefore, there was complete gridlock, even though they had switched direction of flow on the freeway. And actually, in this situation, the evacuation itself became the hazard because people were literally trapped in their cars in brutal heat, and there was, I want to say at least a dozen people actually died during the evacuation because it wasn't properly planned out and executed, because people were stranded on the side of the road, had run out of gas, or had run out of food and water, right? So again, I think that response activities are the hardest to plan for because there's so many factors that are way outside of your control. And then a little bit more about recovery. So recovery is really focused on restoring vital systems that can expedite the return to normal life, like setting up temporary housing, clearing debris, and rebuilding or repairing damaged infrastructure. Here we see some people hard at work in Puerto Rico trying to clear up the damage that was recently done by Hurricane Maria. And look at that, man, what a mess. Can you imagine what that effort's going to take to get the area cleaned up?
I don't want to know.
Oof. So let's talk a little bit more about how we actually measure things, right? So how do we quantify hazards? There's a lot of different ways. I tried to break them up into kind of some of the more typical questions that you would consider and that you could measure. So for example, frequency, how often a hazard of comparable magnitude occurs, right? So here we can develop statistics like the frequency of the formation of a Category 5 hurricane in the Atlantic Basin is on average once every 3 years, right? There you go, useful information to know. Duration is another thing, right? How long the hazard persists. So in the case of Hurricane Katrina, there were hurricane-force winds in New Orleans for less than 24 hours, right? So it's good to know, right? How long is this thing hanging out? For Hurricane Harvey, most recently, the duration was long. It sat over Houston for a long time, which is why I was able to drop such an incredible amount of rain on that region.
Yeah.
Aerial extent, another important thing to consider. That's the space covered by the hazard. So, for example, there's the Gap Fire in California when I lived out that way, and it burned almost 10,000 acres. Pretty small compared to what those wildfires in Sonoma County and Mendocino County and Napa County are doing right now. You have your speed of onset to consider, so your time between the initial hazard appearance and its peak intensity. So you think about like a hurricane, you got days in between when you know that hurricanes come in and when it has its peak intensity over the populated areas that you're concerned with. For tsunami, you might get a few hours if there's an early warning system in place. If there's not an early warning system in place, you might get a few seconds of noticing that the ocean is receding before a giant wave comes in. Actually, they're not even giant waves. It's just a lot of water. So it's interesting. It's not, you have this picture in your mind of a tsunami as like a 40-foot wall of water.
Like the movie.
Right, but the reality is that the ocean recedes, and then all of a sudden it just starts all coming in and goes up onto land. Yeah, exactly. It doesn't. The wave does not recede. It continues on and on and on.
Yeah.
And of course, speed of onset for something like an earthquake, instantaneous, right? Again, there are early warning systems in place that might give you a hint as to when an earthquake might happen, or give you a sense that an earthquake is imminent, but you're still not going to know exactly the minute that it's going to strike until the ground starts shaking. Another thing to think about is your spatial dispersion, right? So this you can think about as the pattern of distribution over space where the hazard occurs. So again, back to the wildfire example, wildfire can jump large areas, right? It can just skip over areas because it's, it can be carried as a single spark, carried by the wind to a new location. And also it can change direction in an unpredictable way because it's driven by the winds, right? The winds can change.
Yes.
Temporal spacing, another way to quantify a hazard, and this is really the sequence of events related to the hazard, right? So, for example, for an earthquake, the temporal spacing of events could be ground shaking, followed by a building collapse, followed by a structure fire, and then an aftershock, right? And this would be the sequence that different aspects of different areas of concern are impacted by a given hazard. So let's talk a little bit more about Hurricane Harvey and this pretty amazing image that we looked at to start with.
Yeah.
Aha! I did write, and I got it right, didn't I?
Yeah, right.
Woohoo! Quick plug for GeoInt Systems and Platforms next quarter. I'll be talking about MODIS. So
I'm not a remote sensing expert, so anxious to learn about that.
Yeah, it's there's a lot to learn about remote sensing. It's almost a completely separate domain space than GIS, although they're merging more and more. So let's talk a little bit more just about Hurricane Harvey here. So it was indeed the moderate resolution imaging spectroradiometer, let me say that correctly, MODIS, which is the sensor that is carried on NASA's Terra satellite and used to generate a false color image of flooding along the Texas coast. So the way that they did this is a combination of visible and infrared light. So these would be the MODIS bands 721. So if you were to download your raw MODIS data, which I believe you can from that website, and load it up into QGIS, ArcGIS, Envy, Imagine, whatever software you wanted to, that's how you could really highlight the presence of water on the ground, is through that particular band combination. So by using this data in this way, your water generally is dark blue or black, but your rivers can appear light blue because they've got large amounts of sediment in there, which obviously your sediment has a different reflectance value than just regular non-sedimented water does. And of course, the technique here is change detection, and you use that to spot areas that have been inundated by rainwater and coastal surges. Change detection goes way farther beyond what we've called change detection in this course thus far, where it's just been a visual comparison. You think about having two matrices with rows and columns of pixel values. You can overlay those on each other and do all kinds of mathematical, or clustering mathematical in terms of just band math, or even clustering functions, all kinds of things using that raw data that will allow you to perform your change detection in a much more robust and scientific way than just kind of looking at stuff and being like, all right, here's my slider, right? Slide back and forth, image one, image two. Although that works really well too. So yeah, going back to this image with what we just learned, you can really see kind of that light blue in the rivers there. See how they're a little bit lighter? This isn't very well zoomed in, but you can really see the rivers kind of flowing into the Gulf, and that change. Right. And it makes sense because that's where you would expect it, right? Where there's a lot of, we have a raging river on land carrying a ton of sediment into the Gulf, and then changing that coloration. All right, so let's take a 10-minute break, and then we'll come back and talk about emergency evacuation. All right. We are back. So, moving on, focus a little bit more on emergency evacuation. This is one of my areas of particular expertise, so I'll do a bit of a deep dive into this topic, just to give you kind of a sense of the kind of very rich area of applications that emergency evacuation represents, and kind of some of the more theoretical research questions that can be asked about it too, and can be examined using GEOG. So evacuation is usually the last resort response to a hazard. Shelter in place almost always presents a lower risk. And the reason for this is that the evacuation itself can become a hazard. We talked just a little while ago about that example from, I don't remember if it was Hurricane Ivan or Irma, I believe Hurricane Ivan in Texas, where the evacuation was not planned correctly. There was too many people on the road at the same time, and people actually died because they were trapped in their cars in the heat. So bottom line is, issuing a mandatory evacuation order, besides potentially being a hazard to the people that you're trying to protect, it's also emotionally charged and politically risky. People don't want to be told to leave their house, and many people will refuse. And if something goes wrong, as what happened in Ivan, the people who ordered that evacuation definitely end up getting blamed, right? It becomes a big, big issue. Now, coordinating the movement of a large amount of people through a confined space in a short amount of time is inherently difficult. This is a difficult spatial problem to solve. And thinking about it from this geospatial perspective, your spatial scale is an issue, obviously. You really need to consider the location and characteristics of the population that must evacuate, the layout of the transportation network, if you're talking about a evacuation by vehicle, which most of ours are in the U.S., and the area affected by the hazard. And then you have to think about temporal scales too, right? The event speed of onset largely dictates the start and end times of the evacuation, right? So, for a hurricane, when do you order that mandatory evacuation? That's a hard question. There's no easy answer to it. It really just varies a lot based on the characteristics of the hurricane itself. So, for example, for Ivan, because that was a Category 5 storm, it was expected to make landfall as a Category 5, they felt that an evacuation was the best course of action because of potential for huge damage due to the winds.
Yeah.
For Harvey, because it wasn't really a wind event so much as a rain event, they decided not to issue the mandatory evacuation, in part because of the experience from Ivan, but also because the direct impact to people from flooding is a little bit less certain, and also it takes longer to fully materialize.
They had time on their side.
Exactly. Time on their side.
And the governor even got flack for that. It's now coming.
Right. So one way to help plan for emergency evacuation is to create a model, right? A model, very simply, is a simplified version of a real-world process, system, phenomenon, or entity. And your typical emergency evacuation model is going to have one or more mathematical equations that you can solve through enumeration, using an algorithm or a heuristic technique. And I'll talk a little bit more about what those terms mean. Often, when you have these models, you want to solve them many times with a lot of different input parameters, so you can get a whole different host of solutions, and also give your researchers a better idea of how certain inputs can affect the model results. You can also kind of add an element of randomness to a model, which will give you a simulation, a stochastic simulation, and then you can really even better account for the uncertainty within the underlying process, right? So there's always uncertainty with an evacuation. You want an element of randomness in there in your model to really try and replicate this real-world process. Yeah. Modeling these complex spatial interactions between people and their environment is really an important part in doing research for any phase of the emergency management process, but obviously critical for an emergency evacuation as well. So just take a step back. Why would we model an evacuation? The short answer is that mathematical models can inform decision-making during both planning and operations phases of emergency evacuations. And if we can predict where people will be there in hazardous events and when they will be there, the more we can do to protect them, when I think about this from a really big picture perspective. Better model, safer evacuation. Love that animation. So let's talk a little bit about a case study, California wildfire. Definitely a timely topic since the Sonoma, Mendocino, and Napa County fires have been big in the news right now and are the deadliest wildfires in California in quite some time. And it's a good topic to talk about because, well, they happen every year. People have to evacuate from wildfires in California every year, and really across the western U.S. It's one of the unpredictable in terms of location, but very predictable in terms of it will occur somewhere every fire season. Here's a picture from when I lived in Santa Barbara of what this actually looks like. So here you are kind of standing in the parking lot of your local grocery store, Vaughn's grocery store here, and there you're looking up at the mountains just above town, and you're seeing lots of smoke and flames up in the mountains. So not a whole lot you can do about it. Doesn't necessarily need to get your car and start driving far away at 100 miles an hour, but it is a very dramatic hazard to experience because you literally see these flames shooting 100 feet high off of a mountain. So,
yeah, scary.
Indeed scary, especially when it starts getting close to your house. Of course, how people will respond is one of the major unpredictable factors here, right?
Yeah.
So look at that photo on the top left. You can see, there's a wildfire on the hillside right above this woman's house, and she seems to be kind of just walking calmly to her car, like, okay, it's time to leave. Let me go. This wildfire's getting close, and then you can see in the bottom photo, very similar situation with the wildfire up on the ridge, above this house, and these people look like maybe they're freaking out a little bit. And not to say that that's the wrong response. I can totally understand having that feeling when you see those flames coming towards your house. It can be completely terrifying. So some of the research questions that you might ask and want to address through a GEOG analysis. Why do people choose to evacuate from a wildfire? If they choose to evacuate, when will they depart? How do they choose evacuation routes, right? Where do they decide to go? And then the big question you're trying to answer is what strategies will be most effective for improving traffic flow during a wildfire evacuation? So that's really, that third question is the reason for the first two questions. Yeah. One way that you can collect data about people is by doing a survey. One way that I collect data about my class. Surveys are not necessarily the most reliable way to collect data. Direct observation is usually better just because, people don't always tell the truth in a survey. Let's get down to it, or they will misinterpret the questions. There can be a lot of ambiguity there.
Yep.
But for this example, I did an online survey of residents of the wildfire-prone community in the wildland-urban interface and really tried to figure out a bunch of different factors related to travel behavior, risk perception, just basic information and basic demographics. And I searched out respondents by putting door hangers, so just hanging a little flyer on their doorknob saying, hey, fill out the survey. And then I got a hold of an email list as well. And that was another way that I recruited participants. My secondary data, GIS and weather data, right? So my GIS data, I got a really nice data set from the County of Santa Barbara, or was it CAL FIRE? I think it was the County of Santa Barbara, showing the fire location, right? So one of the maps that wildfire mapping teams will have to create continually is fire perimeter map showing basically where the fire is, right?
Yeah.
So I got a hold of those maps. I got some maps showing where the different evacuation zones were over time because they had different zones showing where they ordered mandatory evacuations and when. Digital elevation model, obviously very useful to understand the terrain that the wildfire is occurring on and where people have chosen to locate their houses. Streets, obviously, a really critical GIS layer if you're going to understand a vehicle-based emergency evacuation. People are driving their cars away from their house. Tax parcels, really cool piece of GIS data you can find for pretty much any decent-sized town or city in the U.S. Where you can see where each individual property line is and also get some basic information about the owners of that property. And then the other data that I collected was data from weather stations. So looking at factors like temperature and wind speed that can obviously not only influence what a wildfire does, but also influence how people perceive the risk posed to them. If you see a wildfire up on the ridge and there's no wind and it's kind of cool outside, you might be like, all right, well, there's a wildfire, but it's not going to move towards me anytime soon. Mm-hmm. If there's a wildfire on the ridge and there's a very strong wind, hot wind blowing into your face, you might become a bit more concerned about that wildfire impacting you. So one of the models that I created for this particular project was called a survival analysis. And this is where you model the time it takes for an event to occur, or for multiple events to occur. So one of the more common uses for this analysis technique is to look at time until death for recipients of different medical treatments. So for example, if someone gets cancer, there may be 3 or 4 different treatments that they can apply. And survival analysis would be how you could measure the potential effectiveness of each of those treatments. In my case, I used the survival analysis to basically mean time to evacuation, right? So as opposed to time to death, this was the amount of time leading up to the point where a person decided to evacuate. So via my survey data, I was able to come up with what's called a survival curve. You can see on the y-axis, you have the percent evacuated, starting with 0, starting before anybody evacuated, and then ending at 100%, which would have been everybody evacuated. And then you have date and time across the x-axis there. So you can really see if people decided to leave, when they left, right? So kind of a nice snapshot of how the actual evacuation from this particular wildfire happened over time. What you can do is you can look at different factors and compare the survival curves with those different factors, right? So similar if you want to go back to our time until death example, right? You can look and see how much longer are people alive that receive chemotherapy versus people that don't, and you would have 2 different curves on your chart. So what I did for this one is I made 2 different survival curves for people that did not receive a mandatory evacuation order and those that did, right? So bottom line is that even if you don't receive a mandatory evacuation order, you may still decide to leave. And sometimes if you do receive one, you still don't leave because, truth be told, there is no such thing as a mandatory evacuation. Yeah. They can tell you to leave, but they can't force you from your house. Yeah. So what's interesting about comparing these 2 curves, you can see that people, as expected, people who received a mandatory evacuation order, definitely a lot more of them over time decided to evacuate, right? And you can see actually a very distinct difference between those 2 curves right away during the onset, right? So right away, if people got that order, they were like, all right, I should probably go. People that didn't may have left. Some of them left anyway, but some of them decided to stick around. Mm-hmm. I have some questions related to risk perception in the survey too. Basically, there are a lot of different questions that all kind of contributed to this one factor, but what it came down to was a level of risk perception where they perceived high risk to themselves or low risk to themselves. And again, you can see the people that perceived a high risk were not only more likely to evacuate, but more likely to evacuate early versus those that didn't. Again, to be expected. Another really nice application of this survival analysis technique is looking at the impact of distance, right? How far were these people's houses from the wildfire perimeter at any given time? And again, you can see right away early on at the start of this thing, people that were less than a quarter of a mile away, a lot of them, pretty smartly decided to leave, right? Decided to evacuate. So very, I think this is a very intuitive way to visualize data that has a geospatial component into it.
Yes.
It's not a map, but it does give you a sense of how events unfolded over time and space.
Yeah.
Right? Another kind of cool graphic I made, this isn't survival analysis, but this is just basically plotting a bunch of variables along the same timeline. And also, I guess I managed to match up those values too, which is kind of cool.
Yeah.
So here you can see the actual number, raw number of evacuations over time. You can see the maximum wind speed over time and the air temperature over time, right? And I think it's interesting because you can see a few areas where all three of these factors spike, right? Where the number of evacuations spike along with the maximum wind speed and the maximum air temperature. I'm looking specifically at 1 p.m. on May 6th, where this type of graphic provides some evidence that those environmental factors have an influence on the decision for people to leave. Now, it should be said that, of course, these environmental factors also have an impact on how fast the fire is growing and where it's going to, right? So to say that it was perception of these factors as presenting a risk to people versus the actual physical reality of a fire approaching their house causing them to evacuate, you couldn't really say conclusively one way or the other.
Yeah, well, that's okay. It's just interesting to know.
So one of the cool things too is you can take this measured data, right, where we actually measured when people left, and then you can try and fit it to a known mathematical curve, right? So here we have a Rayleigh cumulative distribution function, which is a known mathematical formula, and you can basically match it to a section of time during our actual collected emergency evacuation data. And basically, you can use this to generalize when you believe people will leave, right? So you can actually say, okay, I'm going to develop a probability model of trying to predict when people will evacuate by just using a mathematical function and then seeing how well it fits my observed data.
Yeah.
And what I did with this probability model is also tried to model it based on high risk perception, a low risk perception, and then a moderate risk perception too, by playing with the inputs to the model just a bit. I don't have the actual equation up here because for the purposes of this class, graphs and charts are good, but I haven't really thrown any heavy math at you.
Yeah.
Although I think I do have a slide coming up that's got some math on it, but I'm only going to talk about it. So don't worry. So here we go. Let's talk about some answers to our first research question. Why do people choose to evacuate from a wildfire? And if they choose to evacuate, when will they depart? So the answers we came up with based on that research was receiving an evacuation order, distance from the fire, and risk perception all influenced those decisions. So that Rayleigh probability model that I showed you, that produces an evacuation response curve very similar to the S distribution. And this is actually widely used by traffic engineers and governmental groups, including the Army Corps of Engineers, when they're trying to predict when people will leave during emergency evacuation. So it's always a good thing when your actual observations, your empirical data, matches a commonly used model used to model the evacuation process. So the next question that we ask asked was, how do people choose evacuation routes? So for this one of the components that we had on the survey was a cool clickable map where you can click on street segments in this map to show the evacuation route that you took. Now, obviously there's some error involved in this. Someone could not remember. Somebody could accidentally click on the wrong street segment.
Yeah.
So it's not a perfect method for collecting this data, and definitely not as good as something like traffic cameras or something like that.
Yeah.
But it was the best that we had available, so we went with it. From the results of that, you can actually produce some maps, right? So on the left is the result of that component of the survey where people clicked on their evacuation route that they took. And for this, I was just modeling one specific area. So you can see this is kind of a small neighborhood that is right in the wildland-urban interface. We step back to this previous map. That's showing that neighborhood. And basically, you're familiar with the Google Maps scheme where everything in green is basically forest, right?
Yeah.
And wildland. So you can see that this neighborhood is right on that edge of, you know, here's where the city is, here's where we're in the woods, right? But you can basically take, again, this observed data through the survey, make a map showing what evacuation routes people took and where they kind of exited this study area, and compare that to a model where you basically calculate the shortest distance from their origin to their closest exit to see how well they match, right? So you can see visually that there's some differences. Then you can actually, you know, make a chart showing where what routes people actually took compared to what the shortest distance route would be, right? So the gray bars show the shortest distance for all the routes that we collected, and then the black bars on top of it show how much longer people went when they didn't choose that shortest distance route. And one of the things that we found out through our survey is that evacuees a lot of times would choose routes with higher speed limits, right? As opposed to the shortest distance, they're like, well, I'm gonna take the higher speed limits. It'll get me out of there faster.
Yeah.
And there's also an interesting factor in this particular study area where there are some private roads. So first, here's an example of the higher speed limit streets versus the lower speed limit street, right? You look at this higher speed limit street, you can see it's wider. It's technically 2 lanes on each side, although you're only supposed to use 1 lane on each side. And there's no curbside parking, which allows you to safely drive faster without fear of hitting your car too.
Yeah.
Versus these 25-mile-an-hour streets where there's curbside parking and they're more narrow. But there also were 2 streets in this study area that are marked as private roads and say that they're not a through street, even though you can get through on it. So interesting factor that you don't get everywhere in the world, but in this particular study area, a very local and specific factor that may have had an influence. So here we can look at where these private roads are located and see that people were actually driving on them, right? And kind of getting a sense of how this could make a difference in terms of people taking the shortest path route or not, right? Because if they didn't know about these private roads or believe that what the sign said, when it said not a through street, was actually true,
Yeah.
they would never know to take it and would automatically take a longer route. So the goal here is to predict evacuation routes people take. Bottom line is that shortest path is a good starting point, but alone not enough, right? We already showed that when comparing our actual observed data to our shortest path data in those 2 maps. So when we're talking about a model, something that accounts for evacuee wayfinding strategies might be able to predict our evacuation routes more accurately. So we really need to account for individual choices, those that were revealed by our survey respondents, to predict this aggregate traffic flow. And of course, we also have to consider traffic congestion too, right? It's not just as simple as going taking the shortest distance, because the shortest distance may not be the shortest time, depending on how many other cars are on the road at the same time.
Okay, well, it's changing. Google Maps does a good job nowadays of displaying traffic data.
Absolutely, yeah. They are amazingly accurate. I've done a lot of tests where I've said, all right, how long does Google Maps say this will take, and then how long does it actually take me? And they're usually spot on.
And how it automatically changes the routes around now.
Mm-hmm.
So convenient.
Mm-hmm. Yeah.
It's not perfect all the time, but it's pretty good.
Mm-hmm.
It's interesting, like, try to trick the system on purpose to see, like, okay, can I beat the system?
Right.
Get it wrong.
Right. Or like, no, I know a faster way.
Yeah.
And then you take it and you're like, Google is probably right.
Yeah.
The thing that Google Maps doesn't account for that I wish it did is, or an option that they might want to consider, is the stress related to a specific route.
Yeah.
Like, for example, there's a lot of different ways I can get home from here, which is great. But the fastest way is almost always getting on the Beltway.
Mm-hmm.
But I don't like driving on the Beltway during rush hour. It's stressful. It's people slamming on their brakes. It's hard to merge. There's all these things.
Yeah.
I can also just take University Avenue from campus straight back to my house, which is slower, most of it, almost always slower, but 5 minutes slower, and all I have to do is sit in the middle lane on one road and get from campus to my house. So it's like, in terms of stress, it's actually a lot less.
Yeah. Now,
Google can only do so much, and of course they are only focused on the time, right? That's it. That's really their sole factor in calculating a route for you, which is sometimes at the expense of stress or the ease of taking the route, right? If you've ever been on a route where they're like, turn left, turn right, and you're driving on all these weird side streets to get somewhere like 2 minutes faster.
Exactly.
I always kind of ask the question of like, was that really worth it versus just staying on the one street and taking 2 minutes longer?
Yeah.
So there's a trade-off there. So I don't want to get too much into networks yet, but I just want to show this quick example of how we can mathematically encode a road network. Again, I don't want to talk about this too much right now because our whole next lecture is all about networks. But the bottom line is there's a mathematical basis for all these models, and it starts with an encoding of a road network. So answers to research question 2, how do people choose evacuation routes? Shortest distance is an acceptable starting point. It's a good general rule, or in Google's case, shortest time, because they have this dynamic traffic information. And that's obviously the result that they pop up every time. It's like, this will take 17 minutes and it's red, right? So I guess it does account for stress in that sense, right? You could choose maybe a yellow route that would take 20 minutes if you wanted to.
True.
How often do you actually do that? Pretty rarely, but I do sometimes. You never know. Some other factors that you want to consider when trying to predict what evacuation route people will choose: speed limits of roads, the characteristics of different destinations, and the knowledge and previous evacuation experience of evacuees. Someone's doing this thing for the first time, probably just going to take the route that they would usually take to get to work or to the mall or wherever the places that they typically go to. Whereas someone with intimate experience of the evacuation process might say, wait a minute, I know a better way, there will be less traffic, and I can get to where I need to go more safely. So you can develop a network flow model to represent a system of evacuation routes with greater accuracy than a model based on shortest distance alone. But the bottom line is it's difficult to fully account for the unique behaviors of individual evacuees when you're doing this type of aggregate model going back to those maps that I showed, right? It didn't have any time component either. It was just like, here is where people went and the number of people that went there, not when. So third research question, which strategy will be most effective for improving traffic flow during a wildfire evacuation? And the method for this one that I used was a micro simulation. So here we can really test strategies for improving evacuation traffic flow because you can model and measure each individual vehicle that's on your transportation network.
Right.
And here you're really capturing your nonlinear or your time-dependent traffic dynamics like queuing, right? We've all sat in a line of cars and seen how it takes a little while after the first car goes for the next one to go, and the next one to go, and the next one to go. And then, of course, back to my driving on the Washington, D.C. Beltway example, when one person taps their brakes on the Beltway, there's usually about 5 or 6 cars behind it that all slow down because they're reacting to that person tapping their brakes. And you can have complete stoppages in heavy traffic just due to the fact that many, many cars are getting stacked up very closely behind one another in a lane and reacting to each other. So the way that I did this micro simulation is used some professional traffic engineering software, vSim, which is produced by German company PTV Vision. So again, we're going back to our familiar network. You remember this that I showed on the previous maps where I was trying to show which routes evacuees took. So same study area, same exit locations from the network. I've got a traffic light in there now that I can actually simulate. And here's the area of detail that I'm showing in a screenshot of this simulation, right? So this is what the simulation software actually produces. You can see here's my road network. Here are each of my little individual cars on there. You see those teeny tiny little red, white, and blue, and yellow cars on there.
That's cool.
So what you get from running a simulation like this is you get these nice graphs showing the number of vehicles that are leaving your study area over time, right? And then you can see the total number of vehicles, the clearing time for the study area, the average delay time in seconds for each vehicle, and the average vehicle speed, right? So all factors that are pretty important to consider when you're trying to figure out how to optimize an emergency evacuation plan. What you can see here is there's 4 different scenarios that I used as well. So basically 4 different simulations that I built. There's this baseline scenario. There's a scenario where you have extra traffic on the network, where there's more cars than you expected. There's a scenario where you open up a new evacuation route for people to take. And then there's another scenario where you have lane-based routing, where you essentially switch direction, the direction that people can drive on certain roads within the study area, similar to that picture of the hurricane evacuation that I showed earlier, to allow people to get out of the study area more quickly because you're increasing the capacity of the road in the direction you expect them to travel.
Yeah.
So here's a couple of key points. Wildfire begins at 4 p.m. 4:10 p.m., the evacuations start. And the time period of concern is really towards the tail end of the evacuation because that is when the wildfire actually burned into this neighborhood, right? So with the new evacuation route, you can see that there are fewer cars in the study area during the later time periods, which is a good thing, right? The critical factor here is to get people out quickly. And you also can see that the average vehicle speed was much faster and the delay in seconds was low. And then, of course, that critical number, study area clearing time of 1 hour and 13 minutes. So vehicles exit more quickly and fewer remain later.
Mm-hmm.
Here's the lane-based routing scenario that we came up with. So you can see here how we're switching the direction of travel on a couple different streets that in the simulation become very congested. So the idea of the control point is that you will need to have people in place to direct traffic. Otherwise, people won't know what to do because they'll be used to be able to drive any direction they want. So another factor to consider that is very tough to account for doing this type of traffic simulation, right? You can't really account for the people on the ground. It's very, very, very hard to do. But anyway, one of the methods that there's been a decent amount of research done on, and like I mentioned earlier, a method that's very heavily used for hurricane evacuations, right?
Yeah.
Almost every state that gets hit by a hurricane has a plan, usually dealing with their interstate freeways that switches the direction of travel. But for a local example, look at the express lanes on I-95, right?
Yeah.
Those are switched to different directions based on what time of day it is and where most of the cars are going. So for this particular scenario, question?
Interesting. Sorry.
For this particular scenario, you can see that the lane-based routing does pretty well. We've got a slightly longer study area clearing time, a longer average vehicle delay time than our new evacuation route scenario, and a slower average vehicle speed. And if we compare it to our previous curve, we can see that there are more vehicles that exit quickly, but more that remain later, right? So people are getting out faster sooner, but there's vehicles that are stuck in this study area till a later period of time, which isn't necessarily a good thing.
Mm-hmm.
So answers to research question 3, which strategies would be most effective for improving traffic flow during wildfire evacuation? So I forgot to mention that first scenario of increased traffic on the network was related to a popular hiking trail in the area where people park on the street.
Okay.
So the idea there was that if a wildfire were to break out on a Saturday afternoon when there's a ton of people hiking up in that area and are parked on the street, you'd have extra vehicles that you would have to evacuate.
Yeah.
So one of the possible strategies that have been talked about was imposing parking restrictions, right? So that you couldn't be parked in that area on the street during certain times of the year, maybe, or certain times of the week.
Yeah.
So the bottom line was imposing parking restrictions, opening a new evacuation route, or implementing a lane-based routing plan could all be effective. Opening the additional evacuation route provided the most significant improvement and might have the fewest political and logistical hurdles to overcome prior to implementation during an actual evacuation, right? If you open up a new road that is just closed right now, it's a lot easier than telling people they can't go hiking somewhere or getting the resources in place to direct people to drive on a road in a way that they've never driven before.
Mm-hmm.
So, the other cool thing about simulations is you can make movies of them. Hooray! So this is a different scenario that I did. This is actually for a location near San Luis Obispo, California, that's very close to a nuclear power plant. So this is a simulation that I built that was, again, thinking about a lane-based routing strategy for evacuation from a nuclear power plant. And this is more of a visualization. I mean, there were some measurements that I took away from it, but this was more of a visualization of what it would look like as opposed to something that was more robustly scientific. As you can see, this type of software is pretty cool and pretty useful. You really do get this photorealistic simulation that I think it captures actual traffic dynamics pretty well. Like it looks pretty close to what, how people actually drive. Of course, the trickiest part of this is in the merging, right, and really dictating how to set up that behavior, because the reality is that no one ever merges doing the my turn, your turn method, right? It just doesn't happen. Exactly. It's a theoretical construct, and when people do it, it's incredibly efficient. But there you can see that white car yield to the red car as you made a left turn on there. Is that really going to happen? Maybe. Depends on the driver. Yeah, I don't know. We'll see. So that is our baseline scenario. And then we can move on to show our lane-based routing scenario, where we've changed the direction of travel on this freeway, so everybody's moving away from the hazard. So one of the cool things, too, is you can at least visualize how your control points might be set up, right? So here we've got our guy standing there with his truck. He's got the road blocked off with his truck. He's got the cones up. And he's saying, all right, you can't cross over the freeway here because there's nowhere to go. Get on the on-ramp and get moving. And then you'll be able to see it on the other side of the highway too.
So cool.
This was fun. This is the stuff that I really like doing. I really like making things like this that have a nice visual impact, because something like this really explains the idea of lane-based routing a lot better than any number of words and black and white graphs ever could.
That's right.
So, questions?
You did this for grad school?
I did this for grad school.
Yeah, that's awesome.
Correct. Ian's headed out. I'm going to type him a response, even though I don't know if he's already left or not, because I wasn't watching the chat window. Okay. Let's come back here. So let's do a very quick demo of R. We did our last QGIS lab, at least for the time being. So the exam was the last QGIS lab.
All right.
Now we're moving on to R, which is a scripting and programming language. It's pretty much the most popular open source language for statistical modeling, and it's really growing quickly in terms of doing big data analytics and spatial analysis.
Okay.
So it's a pretty popular tool. When I was working at AGC, I used it for a lot of different things. I actually had one project for a specific customer where he was like, write some R code for me. So it's definitely catching on more and more. It can be a little bit difficult to use, especially when you have never seen it before. So that's why I just want to walk through a quick demo before we really jump into it with our lab tomorrow. Okay. Just so you can kind of get the basic feel for it down. So I'm going to close this, and let's launch R. This is what the window looks like. So this is kind of a standard command line window, and this is one way to interface with R, right? So this is like, you can, if you've worked in scripting programming languages before, you can do stuff that you would expect to work pretty much anywhere. You can do little print statements where you can say, what's the classic computer science thing? Hello world, right? And then there you go. You've got hello world. You can assign a variable, right, and say v equals hello world. Actually, I don't know if this is going to work or not. This is a good test for me. Now we can say there's v, and then we can do print v if you wanted, but you would know what print v would want. right?
Exactly, yeah.
So it's a dynamic scripting language, right? You can dynamically enter commands in here and do any number of things.
Okay.
It also allows you to store your R commands as scripts, which you can then execute. So here's an example of just a very short script that I saved, right? And kind of saved some of the same commands that I just showed you, right? I've got the print command in there. I've also got some simple math, right? So you can either type stuff directly in here. All right, what did I have? Z equals 1, plus 2, Z is 3, right? Very, very simple, basic stuff like that. So I can either type things in there, I can copy and paste out of here directly into your command window,
Okay.
right? And then that does the same thing, right? It's just easier because then you can actually save stuff instead of having to type it in, worrying about little typos and weird other things that can screw you up. So that's so it's a very handy way to build a script to enter commands in here step by step and then save them into your .r file.
Okay.
What I'm going to have you do for the lab, just to start with, is to open this .r file, which is how you save all of your scripts, and just copy and paste commands into the window, because that way you can see how each one of those commands works and get a sense of how you could build a more robust program, if you want to call it that. I mean, I don't really call this is not really a program. This is more of just a script. It's more of a series of commands that you want to run in a certain sequence. So one other thing to note, I'm doing this on a Mac. The built-in tool for handling scripts on a Mac does some nice things like using different colors.
Yeah.
The built-in tool on Windows doesn't do that. I don't know why, but it just doesn't. Everything, when you open up a script using the default R tool in Windows, it's all just black and white, which can make it very hard to read. So for the lab, what I'm having you do is open the .r file using Notepad++, which is a really nice tool for any kind of coding you're ever going to do, because it can handle pretty much any programming language.
Oh, okay.
And the advantage of it's free tool. It's already on the machines, the lab machines. The advantage of doing that is when you open the .r file in Notepad++, it will give you some nice coloring like this, so you can see the different sections more. So, one other thing you can see here, this is how you put comments in, right? So this is just a kind of a classic comment. So like, put this in here, and that's it. It doesn't do anything, right? It's not going to throw an error. So literally, it's just for comments in your script. So the stuff that uses the hashtags doesn't get actually executed when you run the script. So I should mention too, you can also run a script by going up here and saying execute, right? So that's how you would run a complete script all in order if you want to do that, as opposed to the copy and paste method. So that would run every command in here.
Oh, you don't have to highlight it. You just have everything laid out in the window and you just hit execute. I
think you do have to highlight it actually, but that's, I mean, you had,
well, that makes it easier. I'd rather have to do that anyway.
Right. So you can, and this way, I mean, you can execute it line by line too, right? Mm-hmm. So I can go here. I have the shortcuts memorized. The shortcuts are way easier to do. It's command return for execute, right? And then I can just execute that line, or I can go here, execute these three. So all this stuff is fine, but this is like, okay, I can add numbers. I can print GIS is cool, right? Kind of boring. The power of R is in all the different packages that you can install for it. So you can find a package in R to do pretty much any type of analysis that you want to do. So I walked through this in the lab, but the first thing that you need to do whenever you are working with a new install of R, like once you have it installed on your system and you have packages installed, they'll stay there. But for a new install or for those machines in the lab, which get wiped, all the time, nothing really gets saved on there except in your specific user workspace. You have to go and make sure that your packages are installed that allow you to do the analysis you want to do. So there's this function called package installer. You go in here, you get your list of all your different packages that exist. You can see there's a ton of them. And then once you find that package that you want, and I definitely tell you which packages to use in the lab. So this is just kind of an example of how to load that up. So you're starting ahead a little bit. Well, let's say I want the ACC package. I have no clue what the ACC package does, but I'm just going to pick it randomly. You highlight it, you hit install dependencies, because a lot of times these packages, these libraries of functions will rely on other packages as well, and you hit install and selected. And like I said, I don't know what the ACC does at all. I don't know how long it's going to take. It might take a little while to install it. It might completely crash R. I don't know. Packages, anybody can build them. So it's a little bit of the wild, wild west.
Yeah.
So again, kind of the classic thing with open source software, right? It can do pretty much anything. So what you can see now is when I hit install packages, I'm going to go in here. I'm going to install all of these different, right? So this is now installing the dependencies as well. It's pointing to this URL. So when you set this up for the first time, you'll have to tell it where to look for the packages too, and it'll just have a bunch of different sites that you can choose, which will be pretty clear cut. And then it just goes automatically downloads and installs all this stuff, right?
Okay.
And it'll throw up an error if this doesn't work for some reason. What you can do too is if you go R project ACC package, see if this works. And there you go. Now we can learn what ACC does. Processes accelerometer data from unit aerial and triaxial devices and generates data summaries. That could actually be kind of cool, right? I mean, this is like how if you had an accelerometer sensor somewhere and you wanted to process the data, this is how you do it, right?
True.
So, yeah, and like I said, there are an incredible amount of freely available packages that that are specialized to do pretty much any type of analysis.
That's awesome.
Yeah. So and this is really the power of R. This is where the power of R comes in. Is people build all kinds of built-in functionality.
Yeah. There's smart people out there.
There's a lot of smart people that love writing code more than I do.
Yeah.
Once you have your packages installed, you have to load them, right?
Mm-hmm. So
this is this library command, which I'll show you quick. So there's our library. I ran the command. I loaded the rgdal package, which is very, very useful for dealing with any kind of geospatial data. So you remember when we talked about GDAL, right? The Geospatial Data Abstraction Library. This is the foundation that QGIS is built on and that ArcGIS uses as well. So this is your interface to GDAL using R. So basically, you can do anything that you can do with QGIS, but you can do it programmatically through R. Anything
via library.
Yeah.
Okay.
Via this rgdal package, which again you load. Yeah, it's the library function that you use to load that package. If that makes sense.
The package is called rgdal.
Package is called rgdal.
Interesting.
So you'll have to I already have rgdal installed on my computer. I already installed the package. But if it wasn't installed there, you have to go and install it first, and then you run this library command. So now it's loaded, and now you can do all kinds of things. I'll just demo some very simple stuff. Okay. What I want to start with is setting up your environment to work from, right? So you have to tell R where to look for your data and where to save your data, right? If you're, for any package that you're using, right? You're pretty much going to want to do this because you're going to want to save your data somewhere and probably maybe have it load some data from somewhere. So these are just pretty simple commands where I'm creating a variable here and assigning it a path, right? So I'm saying this is my dat directory variable that I am dynamically setting up here, and then what it contains is my path, right? So there we go. Now I go in here, I say, okay, oh cool, that's my path, right? And then I can use this set working directory command, setwd, to tell R that that's where all my stuff is, right? Okay. I'm telling it, this is the directory that I want you working from, right? So now, if I look at my computer now, I can go into, where is this? Here, let's see, R code, right? And I think this is what I just said is my working directory, right? Yeah. You can see the paths on Mac can get a little bit wonky, right? You have to look in the users folder first, and then in your username, and then you go documents and into your subfolder system. It's a little bit easier to set paths on Windows, actually. So now what I can do is use one of the commands, one of the functions that's, I guess it's a function technically. Get my computer science terminology right here. Computer science would be like, it's not a command, it's a function.
Yeah.
Sorry, sir. So we can use, this function called read OGR to read in pretty much any type of vector data. That's what you're going to use, right? So in this case, I'm just basically saying read OGR. I'm pointing it to the directory that I want it to look in, because this command can look in a lot of different directories. And if you can think about the process of reading in data, it could live in a lot of different directories. So it's not, this command won't automatically assume that your working directory is where to look.
Yeah.
And then you just give it the name of the layer that you want to load.
Oh, wow.
And you can load in your shapefile. And so what I did here is I'm running this command, and then I'm basically assigning it to this variable, right? So now I'm creating this variable called countries, which is going to contain my shapefile.
That layer, yeah.
That layer, exactly. So reads it in, OGR data source with driver Esri shapefile. It's telling you what your data source is, it tells you where it is, tells you how many features are in it, how many fields, and then it's saying that we read the area field in as a string for whatever reason, because we couldn't read in a 64-bit integer. I don't know. That's some computer science stuff.
Yeah.
As long as it's not like the bad stuff is when you get error and it's in red, right? As long as all the text is in that black color, it's like, okay, it did something worked.
That's really good. That color, man.
So now countries is in there. We can do something as simple as typing in countries and get all kinds of way more information than we ever wanted about this shapefile, right? I probably should have done that because we might be here for a little while. And this is not even a big shapefile. This is actually a pretty small shapefile. Like, it's giving us all kinds of coordinates, all kinds of junk. This is also kind of one of the downsides of the this shapefile format is that there's a lot in there, right?
Yeah.
It does give you some helpful information, like, hey, look at this. This looks familiar, doesn't it?
Yeah,
at the bottom there, look at that proj4 string.
CRS arguments.
Yep. So, pop quiz. What's the EPSG code for this one?
4326.
Boom. Got it. All right. I like it. So anyway, there's also ways, actually, I'm not sure how well this works with this, but there's ways to access different components of your data too. Wow, this is getting really slow for some reason. I don't know why. So there's this command called, I'm doing a little bit more than what I intended to demo now, but that's okay. So there's a way, this is how you can find the different attributes that are in your shapefile, because the shapefile is actually 4 files. It's got the the shapefile is actually 4 files. It's got the DBF file, which contains all of your data that's attached to the shapefile.
Oh yeah,
right?
when you right-click Open Attribute Table.
Yep.
You see all the things.
Exactly. So this is doing this is basically doing that same thing, but you're doing it programmatically. So here you're saying, what are the different data fields in my countries file, right? And then if you just want to look at one of those fields, you can do something like countries, and then you can use your $sign to subset it, say name, right? And then you get a list of all your country names, right? You can see how these are all indexed as well, right? They all have a number next to them because they're all in order in that DBF table, right? So if you wanted to say, for example, let's see, country, let's do, this thing is getting weird. Country's name, what's in spot number 87? Cote d'Ivoire, right? There you go. So anyway, just a quick demo of how you can find specific things within a bigger data set using R. And then one last command I will show you is our lovely plot command. That's right. Pretty simple to make a very basic map.
Whoa.
There we go. It's tiny. Why is it so tiny? Come on, you. Uh-oh. Now we're getting stretched out. There we go. That looks better. And of course, there are a lot of other different things you can add to plot, things like legends, labels, north arrows,
Do it all through
things
R.
like that too. You can do it all through R. Yep, exactly. So it's an interesting trade-off, I think, between a programmatic approach to geospatial analysis like our programmatic/scripting approach to it. Because, I mean, you can write C++ code and create your own R libraries if you want to. Like, that's how a lot of them are built, and that's what's running under the hood of this thing.
Yeah.
But there's a trade-off between a programmatic approach or scripting approach like this, and then a graphical user interface approach like QGIS or ArcGIS or any of your typical softwares, where there is a lot of overlap between what they can do, but there's definitely some things that are way easier to do in scripting, and some things that are way easier to do using the graphical user interface.
Yeah.
What I found through a lot of experience is that any type of analysis, especially something that you want to be able to recreate easily later and explain step by step how you did it, usually I like to use R for that, because I've got that very explicit record of everything that I did and all the data sources, and I can really dig into my data to a level that is harder in a desktop GUI system. But for the final product, for the graphic design, I almost always choose the GUI, right? Because, like, you can end up with a really nice looking map using this plot command and adding a whole bunch of additional subcommands to it.
Mm-hmm.
But unless you're trying to make the same map 100 times, or a similar map with a slight variation 100 times, right? It's almost, unless there's some reason to automate your map making process, I guess is what I'm trying to say, it's almost always quicker and easier to use your graphical user interface to get everything all aligned and looking good when it's just one, or even 5 to 10. If you were trying to do 100 maps, you needed them all to be almost basically the same.
Yeah.
Or you had some completely replicable analysis process that just took different data inputs to produce that very similar map every time, then you'd probably want to set it up through R. But if it's a one-off kind of thing, it's almost always easier to use your QGIS, your ArcGIS, or even Adobe Illustrator for that matter, to make something that looks really